Um, so yeah, today I'm gonna talk a little bit about automating some federated learning things that we're doing with a system that we're calling FLOX, which is kind of a wrapper around FuncX to do federated learning. I'm not going to give away the main stuff because Nathaniel's going to talk about that a little bit later today. So there's a few kind of main ideas of what I'm going to be speaking on. Like I said, the application is kind of this idea of distributed machine learning or federated learning, specifically addressing the challenges of workload balancing, so the way these workflows can run on different resources, tuning hyperparameters to get the best results, and doing this in a robust way because, as we'll see a little bit later, federated learning, it can be very easy, but it can also be very not easy. And if it's not done exactly right in some cases, especially with very sparse data, you're going to get very, very poor results. So for those of us who have never seen federated learning, just a very quick overview. The idea here is that you have data that lives in multiple different places, and for one reason or another, whether it's data privacy reasons, network bandwidth, or even storage practicality, you can't move that data from where it's created or from where it's being stored to a centralized location to do kind of traditional centralized machine learning. And so you need to learn those features independently at those different endpoints, and then aggregate the learned features in the models to some centralized location. We think serverless makes this very easy. And so we've started to build a framework on top of FuncX/Globes Compute that addresses most of these challenges. Some of the challenges being portability, interoperability. So if you have data living on a lot of different endpoints, obviously those different endpoints are going to have different qualities in terms of compute capability, different architectures, even possibly different network connectivity abilities. So the abilities that excuse me, that FuncX/Globes Compute offers of being able to have these kind of modular fire and forget functions where you can just send off the quote unquote most important tasks of federated learning to these different endpoints and then return the results whenever they're ready. Makes it really simple. And one thing that we found in the federated learning space is you really do need to be simple, because the simplest case of federated learning is basically just taking a dictionary or a list of weights of different models and doing a simple average over all of them. And that's something that's obviously extremely trivial. And that's where a lot of people start when it comes to federated learning. And so you have to be simpler than that. Now, of course, federated learning, as we'll cover a little bit more, becomes very, very complex very, very quickly. But you need to kind of undercut this level of ease at every stage of the federated learning workflow development process. So like I said, we've started putting together this wrapper around FuncX to enable federated learning that we call FLOX, and the logo for which is currently under debate. This is my proposed logo. I'm sure you'll see a different one later. So one of the first challenges is workload balancing. Like I said, serverless enables the easy use of many different devices that are going to have way different capabilities, way different data availability. And so we really want to figure out a way that if you are running simultaneously on a endpoint that has, like a DGX box, a bunch of GPUs, versus an endpoint that is maybe a Raspberry Pi or something that's equivalent, how can you utilize both of those endpoints at the same time in the same workflow without being massively bottlenecked by one or the other? So there are kind of the main way of doing this is to train for a certain number of samples or epochs, such that the product of those two, since they scale rather linearly, is roughly approximate to the capabilities of each of those endpoints. And so we can do this, and we see that whether we balance on samples, so that's reducing the number of samples to match the relative compute level of an endpoint, or balancing on epochs. So again, reducing the number of epochs so they balance based on the relative compute capability. We see basically basically even results across all of the endpoints. So we're not getting major accuracy degradation, and we're able to enable it such that each of the endpoints returns its result at roughly the same time, which really is the most important thing. Now, there are interesting other directions that we can go with asynchronous federated learning, where maybe your federated learning rounds, so the rate of weight exchange is happening at different times for each of the endpoints. But that's, again, one of those much more complicated things that we will address in the future. So another aspect of this is kind of the auto tuning. So if we have all these different hyperparameter factors, how do we tune these such that they work well on the different endpoints, especially with respect to the different amounts of data that you might have. As we'll address a little bit more, the level of data sparsity and non-IID-ness of data across these different endpoints that you commonly see in federated learning. You very much have to be careful with how you tune your model and model hyperparameters. 1 minute, perfect. And so we want to do this very carefully and very targetedly. But again, we want to automate it away from the user because federated learning should be simple. So a practical use case, here's the example, is this was from the Wellington camera trap data set, which is a bunch of camera traps around Wellington, New Zealand that take pictures of wildlife. The data is very sparse. It's very hard to see the animals as a human, let alone a simple machine learning model, and it's very IID. So without any interesting auto tuning, you're going to get very, very poor results. And again, we want it to be simple. So generalizing, if we have this ability to place these federated learning functions anywhere, we want to be able to place them anywhere and even move data if possible. So this is kind of the ultimate goal, is to push data and push compute wherever it seems best. We have a system called Delta, and so we want to integrate this idea of Delta, where we can push these functions and push data wherever possible with these federated learning workflows. So this will kind of allow us this large ecosystem of compute and data sources where we can train, we can transfer, compute where the data lives, or compute where the data isn't and move the data where it should be. It kind of allows for a hybrid structure of traditional distributed ML across different HPC resources. And again, this is all enabled via the awesome abilities of FunkX/Globus Compute. I'm out of time, so I won't cover future work, but we can go back to that if possible, and I will take any questions.
Yeah, you have an easy one. So what's the future work?
I love it. Yep. Yes, so the biggest thing is what I mentioned in the last slide, is this idea of kind of a hybrid hierarchical FL with this distributed ML. So as we have increasingly large ML workflows, models, there's definitely a use case where we can utilize multiple HPC centers at a time. And so you can kind of imagine traditional distributed training, thinking like, that would be enabled across one single system, but now we can do the distributed training and then FL across those different systems. And so that's a really interesting kind of large scale use case that we're interested in exploring that isn't traditionally tackled by traditional distributed ML or traditional federated learning.
Okay, any other questions?